No, of course not. I'm not trying to confuse you, but it is very easy to get confused about all these symbols. So let's go back and take a closer look here. Our beta 1 was given to us by capital S sub xy over capital S sub xx. Remember, capital S sub xy is the sum of our mixed product x times y minus n times x bar times y bar. So let's look at that and see what that looks like. And in terms of the kinds of things you see right here, there's another way that you could have done this was sum xy minus sum of x times sum of y over n. Right, it's the same thing as that. So it all depends on how you want to process your data here. And so that's going to be equal to 3093.33 minus our sum of x, which is 226.3 times 227 all over 17. Right, and that's going to be our 71.6, and that's what you see right there. Right, and likewise, you get capital SXX the same kind of way, and so your beta 1 is just the ratio of those two, and that's where we get 0.9047. Of course, you could presumably have that out in a longer form as well. Right. And then likewise, we can go get our intercept value for y bar minus our point estimate of beta 1 times our x bar. And that's how we end up calculating those specific values that you saw in the chart, and you see up here in our table as well. Now there are a couple of other things that you see here listed out. For instance, this S sub b, this r squared, ss air, and note that this number here at the sum of these squared air terms turns out to be the same as that one too. So let's get into that a little bit. And one thing of interest is estimating the variance of our air. And the true variance is our sigma squared value. Our unbiased estimator of that is then the little hat for the estimator is our capital SS sub e over n minus 2. Okay, now remember that what we're working with here is y sub I is equal to beta naught plus beta 1 times x sub I plus our air term. Right, and then our SSE value, remember, that's our air sum of squares, right? So that's our associated with our air and the sum of those, so our y sub I minus our predicted y squared. Okay, and so what we're really getting here is that there's our air term, sum of all the e sub I squared, right? And that's what we really have up here, and that's what I've done in this processing of the residual. I've come up with our model, here's x, and process it through our expression here and here, right? That gives me y hat, right? And then the difference between y sub I, the actual 116.7, and what we get out of there is our 1.91, our air, or residual, the leftover stuff, right? And then that's squared. This is a long process, not computationally efficient to do that, and so a much faster way to do this calculation is that the air sum of squares is also equal to the sum of squares of the total minus beta hat 1 times capital sub s x y, right, where this total is really the same thing as capital S sub y, right, because The alphabet soup, I know, is crazy. Right, this is the total sum of squares of the total sum of squares, and we get that from the sum of y sub I squared minus n times y bar squared. And that's where that comes from. Right, and so this is a computationally much more efficient way to come about calculating this, or you can do it up here, and you will get the same numbers. It just turns out that I didn't give you the print out the same number of decimal places, but those will be two identical numbers, presuming that you've kept digits the same in the processing of both. Right, and this S sub E is nothing more than the sample standard deviation of the error. So that's just square root of that, and of course then you take this and put it in there. Right, the n minus 2 is there because we processed the data now a couple of times to get to this. Right, we processed it once to get to sample averages, and then we processed it again to get these values, so that we have this model that then we come in with this error. So effectively that's some of a practical kind of interpretation why you see that. Right, now the whole business about the R value that you see there comes from the sample correlation coefficient, which should be interpreted in a similar manner as our population correlation coefficient that we talked about before as well. And so it will be between plus and minus 1, and it gives us some kind of idea of the potential linear relationship that is statistically showing up between two joint variables. And your textbook likes to use a capital R, which I don't prefer. I like to use lowercase r because sample statistics, when they are the final thing, like this one, sample standard deviation of the error is a lowercase s sub e, sample standard deviation of x, lowercase s, those sorts of things. I prefer a lowercase r here, but your textbook uses capital R, so that's what I'll show you. And that's equal to s sub xy, that's a capital, and then the square root of capital S xx and capital S xy. Alright, so that's standard deviation of x, standard deviation, of S sub yy. Good grief. Right, easy to get that messed up, and I just did right there. Standard deviation of x, standard deviation of y, take the product of those and the square root. And so we're normalizing then this mixed capital S sub xy, calculated just like you see up here, right? And so that's some sense of a spread, a mixed product spread. It's a linking, right? That's what this is doing, is linking the x and the y's together, normalized by the spread of x alone and the spread of y alone. And that's our sample correlation coefficient. You see in the chart an r squared reported, and there's going to be a reason for that that we'll see later on, but 0.916 is the sample correlation coefficient. And that indicates a potentially exceptionally strong linear relationship between the two random variables.